Welcome back, grade 8, to another math video. In today's math video, we're going to take a look at similarity. Similarity is similar to congruency, but there is a minor difference. So if we take a look at these two triangles, we would not be able to say that they are congruent. Remember that for something to be congruent, it needs to have the exact same angles and the exact same side lengths. In the example that we have here, we have triangle ABC and triangle PQR, and we can tell already that triangle PQR is much larger than triangle ABC. But if we take a look, triangle ABC and triangle PQR, they all have the exact same angles. So angle A matches up with angle P. They have the same symbol there. Angle B matches up with angle Q. Angle C matches up with angle R. And so what triangle PQR is a scaled up version of triangle ABC, or what we call an enlargement. And when we have triangles like this, when we have shapes like this, we would say that these triangles, instead of being congruent now, are what we call similar triangles. We would say that triangle ABC is similar to triangle PQR. If you remember from our previous video on congruency, we used a symbol to show that something was congruent. We used an equal sign with a squiggly line above it. To show that things are similar, or similarity, we take out the equal sign. So we just have a squiggly line to say that triangle ABC is similar to triangle PQR. And triangles or shapes can be similar to each other as long as they are just scaled up or enlarged versions, or scaled down or reduced versions of them with still the exact same angles. Let's take a look at a rule associated with similarity. We could say if two triangles are similar, then these two things need to be true. 1, the ratio of their corresponding sides are equal. Okay, so we're going to get into this in a minute, but what this means is that when I take a look at these two triangles, every side length has to be scaled up to the same amount. So for example, if this is twice the size, if this side length was 2, then this one would have to be 4. And everything would have to follow that same pattern of doubling up. Or what do we multiply by to get to that next side length? If this was 5, I'll give you a minute to think about what QR is going to be. If we had to double to get from 2 to 4, think about what this new side length needs to be if this original one is 5. Remember, this triangle is twice the size, or 2 times the size. And so, yes, this would be 10. If this was 3.5 or 3.5, we double that to get to this new side length, and we get a side length of 7. So this one is what we would call an enlargement of triangle ABC. They are similar triangles, and the ratio of their corresponding sides are all equal. So in other words, this one multiplied by 2 to get to this side multiplied by 2 to get to this side, and this side multiplied by 2 to get to this side. Those ratios, that multiplying by 2 was consistent. Second, all the corresponding angles are equal. So this is what we've already done in matching things up. We've said that angle A matches angle P, angle B matches Q, and C matches R. And so if these two things are true, then we would say that we have similar triangles. Let's go back to this point number 1 here, because we're actually going to be doing most of our math when it comes to similar triangles is going to involve figuring out missing side lengths, figuring out what's there, and we use these ratios in order to do that. So we could say here that we're going to compare similar ratios. To figure out the ratio, I take side length AB, and I'm going to divide it by side length PQ. You could do this the other way around as well, as long as you're consistent. It doesn't really matter if you're comparing this triangle to this triangle, or if you're going the other way and comparing this one to this one. In this example here, if I were to compare this ratio, I would end up getting a side length of 2, AB, to a side length of 4, PQ. This time, and when I'm comparing it this way, you're going to see that I'm actually going to get a ratio of 1/2 or 0.5. This would be as if I'm going from this triangle back to this triangle. In other words, this one is half the size of this one. Or if I'm going the other way, this one is twice the size of the smaller one. It doesn't matter which one I take a look at. But what's interesting now, so that's 2 to 4, or as we said already, 0.5. That's the ratio at which they're changing. When we compare these two, it's going to be the exact same as if we were to compare any two on here. So side length BC compared to, or as a ratio of, side length QR, which is 5 to 10, or 0.5. And then if we take a look at the last one, AC to PR, or 3.5 to 7, which is 0.5. So once we know this bit of information, we can actually use that to solve missing side lengths. And so this would be our answer to rule number 1. The ratios of the corresponding sides are equal. If two triangles are similar, this shows us that number 1 is true. Number 2, we're showing all the different angles that are equal. And so what we do is we actually use the symbol, we say M angle A. So the M just stands for, this is a measure of angle A. So the measure of angle A right here is going to be equal to, which angle is angle A equal to in the second triangle? Yeah, so it's the measure of angle P. We would also say the measure of angle B is equal to the measure of angle Q. Those are the two that match up. And then the measure of angle C is equal to the measure of angle R. That's the one that C and R match up. So this first part here, this shows that the ratio of the corresponding sides are equal. The second bit that we have here shows that all the corresponding angles are equal, and therefore we can make this statement that triangle ABC is similar to, note we have the different sign now than congruent, similar to triangle PQR. Now that we know this information about similarity, let's try to do some math questions associated with this. If you feel like you grasp it really well, you can either keep listening to this video, or you can go through and you can see the examples on your own in PDF later on in this section. But if you'd like to listen to the explanation, we're going to go over example 8 and example 9 about similar triangles. So example 8 gives us the question. It says, in the diagram, triangle ABC is similar to triangle PQR. All right, so already we have a bit of a tricky piece here. And the tricky piece is that these are mirrored or flipped images of each other. And so we say that triangle ABC is similar to triangle PQR. What that means is that A matches with P. Notice how they're first here. B matches with Q, and C matches with R. So they are a little bit of a flipped version, which might make it a little bit trickier in this question. It also gives us the information that AB, the side length, is 6, that BC side length is 4, and that angle, the measure of angle, it says BAC. Whenever we have 3 letters in there, we're really just concerned about the middle one. So although it says the measure of angle BAC, we're really just looking at that middle one, that angle A, which starts at B and ends at C. So angle A is 24 degrees. And PQ is 5 centimeters. So the first question says find angle QPR. the measure of angle QPR. So if you remember from before, when we have 3 letters here and we're looking for an angle, we're really just starting at Q, going to P, and then going to R. So our angle is really only at P there. So we're starting at Q, going to P, going to R. So this is the angle that we're looking for. And if we take a look at our other triangle, P, the first letter here, matches up with which one? Matches up with the first letter in this triangle, which is A. And in similar triangles, if I know angle A, angle P has to be exactly the same. So, find the measure of angle QPR. Well, angle P is going to be equal to angle A, which is 24 degrees. They're similar triangles, so all their angles must match up. Let's take a look at question B. Question B says, what is the length of QR? Okay, so this is what we're trying to find now. The length of QR, we don't know what it is. We can use our ratio of corresponding side lengths, though, to figure that out. So first questions first. Side length RQ matches with what side length over here? Well, RQ and CB, they match up. So what we know is that we're going to take a look at the ratio of RQ to CB. That's one of the ratios that we're going to do. And in order to solve for that ratio, we need to use one that we already know, one that we already have information on. And that's going to be these two right here. That's going to be PQ, which we know to be 5, and BA, or AB, doesn't matter the order that you put it in, which we know to be 6. The reason why we're comparing it to this one is because we know both pieces. We're going to use corresponding side lengths that we know both bits of information for to solve for whatever is missing. If you're still a little bit confused, let's put some numbers to this, and hopefully that'll start to make some more sense. So obviously RQ is what we don't know. That's what we're trying to solve, so we're going to keep that as RQ. But let's plug in the numbers for whatever we do know. So CB. CB, if we take a look at our triangles, is how large? Side length CB. And we see that that's 4. So we're going to put that in as 4. Equals PQ. We know what that is. That's 5. Right there. And then BA, or AB, right here, is 6. Okay, well now I have a bit of a math question. And if you're confused by the fact that it's RQ, don't be. You could just as easily write that as X, or write that as any other missing variable, or question mark, or star, or a box, or whatever you need in order to solve for that missing variable here. Now many of you may have remembered this from earlier in the year. We're going to be using this quite a bit when we're solving for corresponding ratios. But when we have a question like this, where we have a setup of 2 fractions on either side of the equal sign, we can start, in this case we're going to start with what's down here. We're going to go across, or diagonal, to multiply, and then divide going down to solve for what's left. Some of you may remember this as kind of the fishy method as we go through in solving this particular question. And so we start off, we do 4 times 5. We start off multiplying across there, which is going to give us 20. And then we're going to divide, so 20 over 6. And that's going to help us to solve for the rest of this particular question as we look to get an answer for what side length QR is going to be. And so in this example, that's going to give us an answer of 3 and 2 over 6, or 3 and 1/3, if I simplified that. Right, 6 goes into 23 times. I have 2 left over. If you're using a calculator for this, then chances are you'd round off at about 3.3, repeating forever and ever and ever, which is fine too. So that's how we figure out the missing side length in this particular example. Now let's take a look at one more example, one that might be a little bit more challenging. In this example, we are not dealing with triangles anymore. We're dealing with quadrilaterals, although the same rules still apply. So in the diagram here, we would say that quadrilaterals ABCD, so ABCD is similar to TXYZ. So once again, we are seeing that they are not just shifted versions of one another. In fact, they are rotated versions. So in our last one, we had a flipped version. This one is a rotated version. And we do have a bit of information here as well. So we see that side length AB is 3, BC is 6, TX is 4, YZ is 6 2/3. Now that's going to be a bit trickier because we're throwing in a fraction here. And the measure of angle ABC is 106 degrees. So the first part of this question that we're going to try to solve, part A, is going to be what is the measure of angle TXY. And so really the only thing again that we're concerned about is the X, and the X corresponds with, in this case, the B, which is the only angle that we do know. So because they are similar quadrilaterals, if angle B is 106 degrees, then angle X must also be 106 degrees. They have to be the same. So that one was nice and easy to get out of the way. Let's deal with a little bit of a trickier one now. B, we're going to deal with the length of XY. Okay, so we're dealing with this long side length here. First things first, what does this long side length correspond to in this triangle, or this quadrilateral? And if we were to rotate it, or if we were to take a look over here, we would see that side length XY, which is what we don't know, corresponds to side length BC, which we do know as 6. Now, in order for us to solve for this here, we need to come up, or we need to find side lengths here, corresponding side lengths that we know both pieces of information for. So if we take a look, we can see that AB is 3 and corresponds with XT, which is 4. Now here's my question. Do I put AB on top, or do I put the AB on the bottom? This isn't something we've talked about yet, but normally, if this was your first thing putting down, doesn't actually matter. The only thing that does matter, though, is that you're consistent with what's here. Because I've already created a ratio where my second triangle is on top and my first triangle is on the bottom, I want to be consistent and stay with that idea. So, in this case, I want XT to be on the top, and I want AB to be on the bottom, so that my triangle number 1 is both on the bottom, triangle number 2 is both here on the top. Now let's plug in the information for the numbers that we know. XY we don't, that's what we're still trying to solve. Over BC is 6, XT is 4, and AB is 3. All right, now that we have these pieces of information, let's start plugging in, or let's start solving. So if you remember, we're going to go across to multiply, we're going to divide going down, and then we're going to figure out our answer once we've finished that part of the question. So 6 times 4 is going to give us 24. Then we do 24 divided by 3, going down now, which is going to give us an answer of 8. So what that means is that side length XY equals 8. That's that missing bit of information there that we did not know before. Okay, let's go to one last part of this question. And the next part of this question is asking for us to solve another length again, but in this case the length of CD. So we are trying to find this side length here, which corresponds with side length YZ. This is where it gets tricky because we're dealing with a fraction. Okay. Usually when we set this up, you'll notice here as well, I try to keep my unknown on the top. If you can, that usually makes things a little bit easier. So we're going to compare side length CD, that's what we're going to try to solve, with the side length that we know, which is YZ. That's the corresponding one on this side, even though it doesn't look like it. Remember that this is a rotated version of it, so that's where they would end up meeting each other. And then let's compare that with something that we know. Now, it doesn't matter now whether we choose 8 and 6 or whether we choose 3 and 4. We know both of those. It doesn't really matter. Let's stick with what we had before, our 3 and our 4. So we're going to say that we're going to compare that with AB to TX. All right, just like we did before, let's throw in our numbers here. Let's throw in what we know so that we have everything filled in except for the unknown, except for the missing variable. So CD is still our unknown. That's what we're asked to solve in the question. We're comparing that to YZ, which is 6 2/3. It's never usually fun to have a fraction in a fraction, but we'll work with that. If you'd rather round that, you can. You can change that into a decimal. You could just say that's 6.6 repeating, or even 6.7 if you need to round that. But for now, I'm going to keep that as a fraction and work with that as a fraction. So equals AB, we know to be 3, and then X we know to be 4. Just like before, we're going to do our little fishy method here. We're going to multiply and then divide in order to figure out what's missing. So as we go through, we're going to start off with 6 2/3 times 3. Again, you could have rounded that to 6.6 or 6.7 and then multiply that by 3. I'm going to keep that as a fraction just because it actually gives us a nice answer, a nice whole answer if we keep it as a fraction. So just to remind you, 6 times 3 is going to be 18. But then when we have 2/3 times 3, 2/3 times 3 is going to be 2. So 18 plus 2 gives us 20 here. Now all I'm left to do is do 20 divided by 4, which is going to give me an answer of 5. And so that's my final answer. That's side length CD. So you could say that side length CD equals 5. And for the most part, this is how we work with similar triangles, particularly as we're looking at comparing some of their ratios of their side lengths.